The starry sky you look up at is an illusion. The brightest star in the Andromeda Galaxy is actually a stellar relic from 2.5 million years ago. Its current state is unknown to anyone, but that is not the most terrifying part. What is truly terrifying is the Parker Solar Probe, built by humanity, which can fly at an incredible speed of 630,000 kilometers per hour. Sounds unbelievably fast, right? Yet, if you were to fly to the Andromeda Galaxy at this speed, it would take 4 billion years. What does 4 billion years mean? It took 3.8 billion years for all life on Earth to evolve from single-celled organisms to humans. In other words, you could rerun the entire history of biological evolution from the very beginning, and the spacecraft still wouldn't have arrived. Even more despairing is the fact that even if humanity one day manages to build a light-speed spacecraft, by the time you get there, 2.5 million years will have passed on Earth. Humanity might have long gone extinct, leaving you without even a home to return to. The universe has set a perfect cage for humanity. Although you can see it, you can never touch it. However, the vast distance is merely the first hurdle. The challenges we must face next are the true impossibilities. Many people might fantasize that with the advancement of technology, we will be able to build wormholes or warp drives in the future. Here, as a science communicator, I must cruelly shatter your illusions. Physics is not science fiction. It is a wall, a titanium wall, with a dead-end sign hanging on it. Let's set aside light-speed spacecraft for a moment and first discuss the issue of distance. 2.5 million light-years. This number might just be a vague concept in your mind. Let's scale down our perspective, and you will feel a suffocating dread. If the Earth were shrunk to the size of a glass marble placed in the palm of your hand, then at this scale, the Moon would be 30 centimeters in front of you, and the Sun would be on a playground about 120 meters away. As for the Andromeda Galaxy, at this scale, it would be 150 billion kilometers away. What does this mean? Even in this miniature model, you would have to walk from Earth to Pluto just to touch the marble representing Andromeda. This reflects the boundless emptiness of the universe, making one sigh that human existence seems like a mere cosmic joke. You might think that distance is not an issue, as long as we are fast enough. Let's explore the propulsion technologies humanity takes pride in. Currently, both Elon Musk's rockets and China's Long March rockets use chemical fuels. Frankly speaking, on a cosmic scale, this type of fuel is no different from setting off a firecracker. To travel to Andromeda using chemical rockets, you would need to use the mass of the entire observable universe as fuel, and even that would not provide the necessary acceleration for the spacecraft. Therefore, we consider upgrading to Hall-effect thrusters, namely ion engines. Although this type of thruster is indeed highly efficient and can emit a ghostly blue stream of ions, just like in sci-fi movies, how much thrust does it actually generate? About the force of a piece of paper falling onto your hand. True, it can accelerate continuously for decades, but even pushed to its absolute limit, it would only reach 10% of the speed of light. How long would it take to reach Andromeda at 10% of the speed of light? 25 million years. And 25 million years ago, the ancient apes on Earth had not yet even learned to walk upright. If you set off in such a spacecraft, by the time you reach your destination, you wouldn't even be sure if the newly evolved species inside the ship could still be considered human. Upgrading to a nuclear fusion engine is a current area of global research and represents the ultimate energy source humanity can currently access: an artificial sun. If we were to attach a miniature sun to the rear of the spacecraft and use the high-energy particle streams generated by nuclear fusion for propulsion, theoretically, we could reach 15% to 20% of the speed of light. This sounds wonderful, but reality is cruel. Even ignoring the journey of millions of years, the fuel issue itself is an unsolvable bug. To achieve such speeds, the spacecraft must carry tens of thousands of tons of deuterium and tritium. This leads to a vicious cycle. The heavier the spacecraft, the more fuel it needs. The more fuel it carries, the heavier the spacecraft becomes. This is exactly what the famous rocket equation describes. Unless it carries a fuel tank as massive as Jupiter, a nuclear fusion spacecraft will never be able to cross intergalactic distances. At this point, someone will surely suggest using antimatter as a propellant. Through matter-antimatter annihilation, a 100% mass-to-energy conversion rate can be achieved, which is considered the most powerful energy source permitted by physics. Indeed, theoretically, an antimatter spacecraft could accelerate us to 70% or even 90% of the speed of light. But this is precisely the universe's greatest dark humor. Do you know how expensive antimatter is? Currently, the cost for humanity to produce antimatter is about $62.5 trillion per gram. How many tons of antimatter would be needed to accelerate a manned spacecraft to half the speed of light? Even if we sold the entire Earth, the funds obtained would hardly be enough to purchase sufficient antimatter fuel, perhaps not even enough to fill the fuel tank. Furthermore, antimatter is extremely unstable. If even a single atom leaks, the spacecraft will instantly turn into a cosmic firework. Therefore, embarking on space travel with a few tons of antimatter as fuel is not called exploration. It's called playing poker while sitting on an ignited nuclear bomb. Let's imagine that if God granted us infinite energy and immortal bodies, could we build a spacecraft that approaches the speed of light? For instance, using a Bussard ramjet to directly harvest hydrogen atoms in space as fuel. When our spacecraft accelerates to 99.9999999% of the speed of light, congratulations, you have triggered the most terrifying mechanism in the universe, time dilation. According to special relativity, the faster you move, the slower your time passes. Flying at such a speed, you might reach the Andromeda Galaxy in a few decades, or even a few years. You could just relax, enjoy a cup of coffee, or take a nap in the spacecraft. And the Andromeda Galaxy would be right in front of you? This sounds very exciting. But in reality, it is pure hell. Because what appears to be a journey of just a few decades to, you could mean millions of years have passed on Earth. When you joyfully send a signal back to Earth to tell them you have arrived, that signal will take 2.5 million years to travel back. By the time the signal reaches Earth, everything from when you departed, including your family, your country, and even human civilization, may have long turned to dust. Crustal movements might have leveled the Himalayas, and the sun might have grown hotter, boiling the oceans dry. Although you reached your destination, you would become an absolute orphan in the universe, with no way home. This profound loneliness of being torn apart by space and time is a fate worse than death. Moreover, there is an even more realistic problem that directly issues a death sentence to manned interstellar travel: our fragile physical bodies. The human body evolved to adapt to Earth's gravity and the protection of its atmosphere. But what must we face during the long journey to Andromeda? First, once outside the protection of Earth's magnetic field, cosmic rays will continuously bombard human DNA like countless microscopic bullets. After spending decades in the spacecraft, human cells will become as fragile as a sieve, bone marrow will stop producing new cells, and cancer will rapidly spread throughout the body. The unavoidable radiation damage requires lead shielding several meters thick, which not only adds to the spacecraft's weight, but also traps us in the vicious cycle of rocket launch costs. Second, a microgravity environment will cause bones to begin self-dissolving, excreting calcium from the body, leading to muscle atrophy and a reduction in heart size. Decades later, when you arrive at a planet in Andromeda, you might have turned into a flabby ball of flesh, unable even to stand. Gravity will crush your fragile skeleton like a steamroller. The third and most easily overlooked factor is psychological breakdown. Imagine being locked in a windowless basement with only a few people for company, not for a day or a year, but for a lifetime. Outside the window is only eternal dead silence and darkness. No sound of wind, no bird song, no sunrise or sunset. Psychologists have conducted experiments showing that in such extremely confined environments, human psychological defenses rapidly collapse, leading to depression, hallucinations, violence, conflict, and self-harm. Perhaps before the spacecraft even flies out of the Milky Way, the cabin will have already turned into a madhouse or a slaughterhouse. Speaking of this, do you feel a sense of powerlessness? Physics locks down speed. Biology locks down lifespan, and economics locks down energy. This is precisely one explanation for the Fermi paradox. Why haven't we discovered extraterrestrial life? It might not be that they don't exist, but rather that we cannot break through. Every civilization is bound to its own star system, like helpless prisoners on isolated islands, only able to gaze at each other across a boundless ocean without ever being able to communicate. However, the most absurd and unexpected twist has appeared. As I mentioned earlier, we cannot reach Andromeda. Yes, we cannot go there, but they will come to us. Current astronomical observation data clearly shows that the spectrum of the Andromeda Galaxy is blue-shifted, which means what? It means it is hurtling towards the Milky Way at a speed of 110 kilometers per second. This intergalactic collision is inevitable. It is estimated that in 4 billion years, the Andromeda Galaxy will collide head-on with the Milky Way, a scene more spectacular than any sci-fi movie. By then, gravity will tear apart the stars in Andromeda's spiral arms, flinging them into deep space, and the two supermassive black holes will begin a dance of death. The night sky will no longer be dark, but filled with densely packed newborn stars and burning gas, as bright as day. Although the universe has not completely abandoned us, it didn't give us the key to walk out of the cage. But it plans to tear down the walls of the cage and throw our neighbor directly into our house. This brings an even deeper despair. In 4 billion years, the sun will become a red giant, and its expanding volume may have already swallowed the Earth. If humanity still exists, we will have to leave the solar system. Whether we go to Andromeda or Andromeda comes looking for us, it seems to have nothing to do with us right now. Therefore, returning to the initial question, even though we cannot reach there, and even though this is destined to be a tragedy, why do we still look up at the starry sky? Why invest heavily in developing the Parker Solar Probe, the James Webb Space Telescope, and researching black hole theories that we may never use? It is like a person in prison who, knowing that breaking out means certain death, still stands on tiptoe to look at the flowers outside through the gaps in the iron bars. This is not about life and death. It is about dignity. What makes humanity unique is not how far our bodies can travel, but that even when our flesh is firmly pinned to the ground by gravity, our minds can reach the stars 2.5 million light-years away. If you knew that a spacecraft bound for Andromeda could never reach its destination, and that departure meant a permanent farewell, when faced with the choice, would you choose to stay on Earth and wait for death, or buy a ticket and march toward death on the path of chasing the stars? Please share your answers in the comments section. In 2025, the duty officer at the LEO gravitational wave detector suddenly jumped out of his chair because observation data showed that a celestial body had exploded twice. The first explosion had just ended when the second one immediately followed, with an interval of less than a few seconds between the two. It was like watching a person die with your own eyes, and then they suddenly exploded again in their coffin. Even more incredibly, they found a neutron star lighter than the sun in the explosion debris. But according to the laws of physics, such a celestial body shouldn't exist. It is so light that it should just be an ordinary star, yet so dense that it must be a neutron star. This is like discovering a piece of ice that is somehow both liquid and solid. That night, 17 observatories worldwide simultaneously pointed their instruments at this region of the sky. In light of this, people began to realize that the universe was showing us an unprecedented way for stars to die. Therefore, if a star can truly experience a second death, how much of our understanding of the universe is actually wrong? To deeply understand the madness of this discovery, we first need to clarify the ways stars die. Before 2025, astronomers believed there were only 3 main ways stars died in the universe: novae, supernovae, and kilonovae. Each has its specific formation process. A nova is a small-scale eruption that occurs when a white dwarf accretes matter from a companion star. A supernova is the core collapse of a massive star at the end of its life. And a kilonova is an explosion caused by the collision of two neutron stars. These three phenomena are like three different methods of execution: the guillotine, the electric chair, and the gas chamber, each distinct and never mixed. However, the 2025 observation results completely overturned this classification system. The observation data from the first few days indicated that this event seemed to be a typical neutron star merger. The celestial body rapidly dimmed and emitted an intense red glow, and spectral analysis revealed it was rich in heavy elements like gold. Furthermore, the gravitational wave signal confirmed that this was produced by the merger of two compact objects. This allowed astronomers to breathe a sigh of relief, thinking they were about to witness a repeat of the historic 2017 discovery and that their papers were ready to be written. But on the fifth day, things suddenly got weird. This kilonova, which should have continued to dim, unexpectedly began to brighten again. Its luminosity increased, and its color shifted from red to blue. Large amounts of hydrogen and helium suddenly appeared in the spectrum. This is like performing an autopsy, and the corpse suddenly sits up and says, "I think I can still be saved." Everyone was dumbfounded. Because the spectrum of a kilonova shouldn't contain hydrogen, that is a characteristic of a supernova. Even more concerning was that these hydrogen gases were moving at a speed of 17,000 kilometers per second, a velocity that only occurs during a stellar core collapse explosion. What did this mean? It meant that what we observed might not be one explosion, but two entirely different explosions occurring in the same place at almost the same time. It's like finding both a gunshot wound and a stab wound at a crime scene, and both wounds were inflicted in the exact same second. One is the internal core collapse of a star, and the other is the collision of two neutron stars. How could they possibly appear in the same place simultaneously? However, a deeper problem emerged when scientists thoroughly analyzed the gravitational wave data. They found a fatal contradiction. The gravitational wave signal indicated that at least one of the merging neutron stars had a mass lighter than the Sunday. This is considered inconceivable in astrophysics because, according to all existing theories and simulations, the mass of a neutron star must be between 1.2 and 3 times the mass of the Sunday. An object with less than 1.2 solar masses cannot collapse into a neutron star. It will only become a white dwarf. This is like finding a professional NBA player who is only 1.2 meters tall. According to all physiological laws, someone of this height could never make it into the NBA. Yet there he is, playing on the court. Scientists were thus plunged into deep confusion. If such subsolar mass neutron stars truly exist, then the stellar evolution theories we have built over the past few decades might need to be completely re-examined. To explain this unprecedented phenomenon, scientists proposed an extremely bold hypothesis, the super kilonova. This model describes a scenario straight out of a sci-fi novel, envisioning a massive star with an unbelievably fast rotation speed. When this star exhausts its life and begins to collapse due to its excessively rapid rotation, its core does not collapse directly into a single neutron star or black hole, as expected. Instead, it fragments into multiple pieces during the collapse process. This fragmentation process might look like this. The rapidly rotating core forms a massive scorching disk, and under extreme conditions, this disk shatters into multiple fragments, with at least 2 fragments each collapsing into a lower mass neutron star. These two newly born neutron stars are extremely close to each other. They are born in orbits almost touching one another, with a period that might be only a few milliseconds. The result is that the moment these two neutron stars are born, they begin a frantic inward spiral and then crash into each other within a few seconds. Therefore, we actually observed the superimposed effect of 2 explosions. The outer layer manifested as a typical supernova explosion. When the star's core collapsed, its outer shell was blown off by the shock wave and expanded. Meanwhile, inside this expanding fireball, the two miniature neutron stars were performing their final death ritual. Their merger generated gravitational waves and released the characteristic red glow and heavy elements. The initially observed red light came from the Kilonova's light shining through the supernova's outer shell. But as the supernova's outer shell continued to expand and brighten, its blue light gradually masked the inner Kilonova's red light, resulting in the bizarre phenomenon we saw of the color changing from red to blue. This scenario of simultaneous birth and death is something we had never imagined before. More importantly, it provides a possible formation pathway for those neutron stars in the universe with anomalous masses. However, scientists remain very cautious, emphasizing that this explanation is far from conclusive, as there are still many aspects of the entire event that do not make sense. For example, if it really was a merger of two neutron stars, we should have been able to observe intense X-ray and radio emissions. But in this observation, we detected absolutely none of these signals. It's like watching two cars crash, but hearing no sound of impact. Something is clearly wrong. Another even more critical issue is that although the gravitational wave signal and the optical observation were close in time, scientists calculated that there is a 2% to 4% probability that they did not originate from the same event. In other words, the gravitational waves might have come from a neutron star merger, while the optical explosion we observed might have come from a completely different star, and they just happened to occur at a similar time and in a similar direction. Although the probability of such a coincidence is low, it cannot be completely ruled out. It's like hearing a clap of thunder and seeing a flash of lightning at the same time. You naturally assume they were produced by the same lightning strike, but it's also possible that two different lightning strikes happen to occur in the exact same second. If that is the case, then this observation was not a super kilonova, but a massive joke the universe played on us, leaving us to verify which scenario it actually is. Scientists now urgently need to find more similar events. They hope that in the coming years, gravitational wave detectors will once again receive similar signals, allowing them to use all top-tier equipment, including this will strongly confirm the super kilonova theory. The significance of this discovery goes far beyond identifying a new type of celestial explosion. It actually reveals that the depth of the universe's creativity far exceeds our imagination. We always try to classify and organize cosmic phenomena, attempting to fit them into preconceived frameworks, but the universe constantly challenges our conventional understanding. It creates things we thought could not exist, and then places them right in front of us to explain. Take precious metals, like gold and platinum for instance. We once thought they could only be formed inside stars, but if superkilonovae truly exist, it means there is another kind of alchemy in the universe. The gold ring you wear on your finger might not have come from the gentle collision of two neutron stars, but from the frantic fragmentation and self-devouring of a star in its dying moments. This story is far more violent and dramatic. Currently, observatories around the world are on 2 4-hour standby, anticipating the recurrence of a similar event. If this theory is confirmed, we will have to admit that our understanding of the universe might account for less than 1%. The laws of physics we think we have mastered might just be a few of the most mundane and boring rules among the universe's many. And as for those extreme conditions capable of creating miracles, we might have only just scratched the surface. Therefore, the next time you look up at the starry sky, remember this story. Behind that seemingly tranquil starlight, a plot crazier than any sci-fi movie might be unfolding. A star might be spinning at tens of thousands of revolutions per second, its core splitting into two parts, which then devour each other within a single second. Putting on a fireworks show the universe has never seen before. All of this is just to tell us one simple truth. In this universe, nothing is impossible.